Well, good afternoon to everyone. Guess we're back and ready to enjoy another ride. So I have some brainstorming for you guys after lunch. So we have militaries who are on the battlefield, police department, police on in action duty, emergency, firefighters, regular person walking going vacation, walking the streets, suddenly some nature disasters happen. Going to the hospital, surgeon does procedure, and something goes wrong during the surgery. Well, brainstorming, what is common between all those what I just said? I'll help you. Injuries. Injuries, traumas, bleeding involved. Injuries, especially not simple injuries that you can stop, put some Band-Aid on it. Injuries related to abdominal wall, thoracic area, were very hard to approach. Injuries when they involved blood vessels, like arteries, veins, the main blood vessels in our anatomical system, cardiovascular, and that's what we get. If you could see, a lot of people get injuries. We don't see only on the news. Thank God, maybe some of them went through all this. It happens, life. I assume, I'm sure you guys survived since you're here in this room. But a lot of people don't survive because injuries is a matter of minutes, hours, or seconds. What do you guys think? Every second is a matter, especially when it comes to certain injuries. And this is right from military times. Although they're talking about militaries, but I apply this to everyday's life as well. 90%, it's a big percentage. People don't survive out of what I just said about those injuries involved on our everyday life livings, and it's a world statistic. And how that happens in attack scheme, we get trauma. What we do nowadays, we put medication Celox. We're going to talk about it right now. And Celox, one of the ingredients they use nowadays in militaries and for emergency use. You have to press on it and keep it there for a certain timing, and they have to remove it later on, of course, when they get to the for the medical wards. Well, it's again about our companies. Who haven't been here, I see some few faces here. Just I might repeat it, but one more time. It's Nojo's company again. Our missions in this condition, new innovative ways, treat unmet needs, and in the medical field and pharmaceutical industry. And as well, as I mentioned in the previous topic, one of our expertise are synergistic combinations of generic drugs as well, and using them and bringing them to the next level of unique applications. This is just combat materials would use nowadays, currently, near future. And this is the most common, like ghost pad, powders, quick clot, Celox. It's a great product, but, not but yet, sorry. What they consisted on. These products are based on polymers. Some of them are natural ingredients you can see from there, like etosan or chitosan, depends how the spelling goes on the internet. And it's just based on skeleton of shellfish, lobster and shrimps we eat every day, but skeleton they use for, it's not only this, but they have another components to it. But this is one of the main components of chitosan. Alginic acid, it's high molecular weight polymer as well. It's isolated from seaweed. That was natural, about nature, somebody questioned here, right? And we were talking about patenting in that nature. But this is not a drug, they consider it as medical device. A little different applies to the medical device compared to medications. So that's why they use the from nature, that you mentioned about nature here, right? That's the nature coming. Kaolin, it's mineral kaolinite, hydrous aluminum silicate, which is part of the ingredients for another hemostatic agents. And zeolite, you get the lava rock. It's good to have some volcanoes at times. So we can at least utilize them for the reason, not just for the energy and other purpose. And we get to the lava rock. Downsides, well, we have helping agents based on those type of ingredients. The downsides on them, to know what we can do better, we need to know what the minuses are. And they are non-absorbable. They granulated certain sizes, could be small, powder size, or whatever size, but it's still granulated and not absorbable. And it's delaying wound healing, because wound needs to, by nature, has to get together, but it doesn't because something in it, right? Foreign body sits there. It does help, but it prevents something. We have positive and negatives here. Exothermic. Some of these ingredients release energy out and causing the burn of the exposed tissue, exposed vessels, burning phenomenon. Hydrosan-based product, they not absorbable, we said that too. And they lead to even necrosis, meaning tissue gets just, dying the tissue gets necrotized. So another thing which effect happens, when you put hemostatics in packing the wound, it's pushing, well, it stops the bleed, but it's pushing on the walls just by pressure. Not any effects of those, just putting in pressure. It's diminished vascularization because it's getting spattered on the vessels and other side effects. Here our company, I have a new slide here again. What are we doing it? On the desk, on the table? Are we doing in small lab rooms? Or are we, nobody asked that question, but I have an answer already. For you guys, just having scientists, and not enough, you need to have a place. This is one of the oldest institutes in Europe, the National Institute. Based on that institute, most of our testing to be done. We did a test on acute bleeding in vivo, meaning on the animal-based, and in vitro as well, and we patented this product, and we call that product Gamma. Trees again. I mean, we need to solve this problem fast, right? Can we do so without trees? Yes. With trees, it's much faster. And it's again an unmet need. It's very important right now in the militaries, in our daily life, as I mentioned, those situations, and for emergencies matter. And again, I'm not going to repeat this again. Yes, we do use trees for our own research and development. Yes, that's for the trees currently and always. And we are the company who started putting trees and they're solving problems in the pharmaceutical industry. Again, trees, we have a problem. We need to solve this problem. Traditional and I wouldn't say not traditional, but tree style, solving problem. New hemostatics. We need new hemostatics, something different. Meaning, or I would say different approach, or new hemostatic, one of those. So what is new hemostatic should be? It should quickly stop bleeding, not as, I would say quicker even the one existing. Something has to be, definitely we should be better, right? It's a tight pressure, but not tight enough to firm, without consecutive surrounding tissue. It's a dilemma. You have to be tight, but not tight enough, so not to cause the damage. Should be used small amount. Why? If you carry bigger wound, that's when you carry the bucket. If you smaller room, you can get a little full of your fist or something to carry in your hand. Not really. It should be one amount, but can match to different sizes. Expandable, something close to that. New or based on some elements which makes that expand. We'll get that point later. Should be immunologically not rejected or not felt by body that it's a foreign body. It should be accepted by body, by immune systems, by tissues, by immune lymphocytes. It should be accepted as neutral or just indifferent, not to be rejected, not to get any reaction or toxicity. And it should be, after you apply to it, should resolve, meaning biodegradable. Previous one, non-degradable. Our product should be biodegradable after applying to, the bleeding stops and has to be disappeared, absorbed without toxicity. Contradictions. So we have contradiction in this scenario. On one side, we have to stop bleeding fast, tamponate, meaning cover this wound firm, same time not really firm enough not to cause the damage to surrounding tissue. And it has to be on the bleeding side, which it can cause, if you're firm enough, that causes ischemia, meaning narrowing the vessels, and necrosis and damage of the tissue, health tissue. And to avoid tamponade, must be firm, and same time must be not firm. That's kind of final verdict on contradiction. Second contradiction, on one hand, well, we have multiple injuries, different sizes, right? As I mentioned, or abdominal, thoracic, or it's a large vessel, femoral vein. One of those scenarios was imminent death. And multiple injury, we would need to use large amount of hemostatic substance for larger, because volume of the wound equal to volume of the powder placed. There's some law involved in it, a mathematical equation. On the other hand, it's difficult to carry large amount. You cannot predict what's going to happen. You're on the battlefield, you have a certain amount, oh, I should have run and bring another one. Or that's what's going on nowadays. They carry a lot of, it has to be some extra amount close by, and should be enough to cover large wounds at the same time. Yes?
Can you make the firmness a function of the clotting and the area where the clotting is taking place? That seems to be a problem.
At this specific area, right? Good point. So the question was, if you have a firmness, but it's not going to wound this wound, it's not going to bleed all over certain areas, it has to be firm applied to that specific area. That's where you have to do manual impaction to direct this to point. Great point. The answer to you is going to be in few slides later, but I will tell now. But you're going to repeat again. Our product has attraction to endothelial cells, because blood vessels, we predict that. Great point. Our vessels has certain layers, and the intima inside of the vessel called endothelium cover. When vessel damage exposed, it's moving there. It's actually dynamic. One of the our examples of dynamic drugs right here in this example. When you put the powder, where the bleeding is, it attracts there. It goes to the bleeding area and sucks by the negative pressure over to the endothelium and attracts. It sucks. It's okay, I'll tell you in advance so you'll understand next slide. It's become powder with blood. It transfers over to gel-like, glue-like consistency. BF, we had the BF6, like, and so the Keynote, one of those, right? Similar. We have the glue, like universal glue, for so many purposes, even for the skin, for the, right, so the gel-like and it's glue-like same time. So we'll get there. You see, you already knew it, good. It's coming. Principles. So principle of rejection, right? And because we want to, when you're having fulfilled like purpose or become a necessary part, the object has to be discarded. And it means complete biodegradation, artificial thrombus, because we create a thrombus. It's not that thrombus meaning clotting. Naturally, we have a clotting system in our body, and it has to start up right when the bleeding starts. But it takes a little longer, or not enough potential, because bleeding is so harsh and speed. So it has to create artificial thrombus at that specific area before natural thrombus cascade comes over and helps with the dissolution. And the thrombus part function has been performed, and even then, fragment, this artificial should be remain in the wound. It's one of them. And the principle of self-organization, that's what we're coming with the dynamicity here, self-organizing. When dynamic is next year, full blown. it gets self-assembled acute substance when it's an active precursor, like gel-like implant, as we just mentioned. The powder form, the moment they touch the blood, they become a gel-like consistency. And in the presence of the blood, right, mixture. And it's tightened at the wound edges, and it's prevent from rebleed. It's starting confining the wounds even getting together.
So essentially, material is just going to form collagen-like matter, right there.
Something like that, close enough, yes. But again, and principle dynamism, where we state characteristics of the object should be changed, optimal in each work, in the case of means of the different size of the wound, with the same dose applied, and it depends from amount of blood was absorbed. Meaning, on one hand, a large wound could be less amount, but usually larger wounds, they damage more capillaries on the vessels area, and more on the largest vessels damage. And more blood comes out, it's this glue-like or powder form, it has a way to expand bigger. It does, because it's like a sponge. Same amount of sponge, you put more liquid or less, you will see another more liquid, you cannot absorb more amount of blood, and it expands to a certain level. But it's different material. Why did I come up with this? Why we should come up with biodegradables? Because there are biodegradables already. Came up on the certain needs, not on the market of pharmaceutical, for different purposes. I just give you the list currently existing biodegradables on the on the market used for different purposes. Some of them have a bifold, and they have two ingredients here: oxybutyrate and polyhydroxybutyrate with hydroxyvalerate together. And the bifold, some of them just monopole, just like a polycaprolate or polylactic acid and polydioxide. Those are like only few are biodegradables used for different purpose. They are around, but we use similar, but our biodegradable more on this level. Bipole, we use two ingredients and some of the other substitutes. Then we want to figure it out, well, biodegradation. If they're biodegradable, how they disappear, how they fall apart, what's going on, what's the mechanism behind it. So there's few mechanisms up here currently exist, 1, 2, and 3. I can read them all, but I want to circle which one applies to our style. It's number 3, cleavage of backbones, where it says here cleavage backbones, linkage between polymer and the repeats units, and it's after this biodegradation happens, they become water soluble and no trace left after they get dissolved.
Most of these biodegradable plastics, for example, they degrade when exposed to ultraviolet rays.
Right.
So what actually causes that cleavage of backbone in this compound there? Because
good point.
It's not exposed to sunlight.
That's what they're trying to avoid all these plastics, and because it takes not years, centuries for them to disappear, right? They just causes persistent cancerogenic effect, right? Good point. And they use ultraviolet lights to make them more degrade under exposition. Here, if I say I put timer here, it's wrong. Remember the dynamism I mentioned there? These polymers, the one we use it in that combinations, they have their own, a quick other point around, bring it so understandable. Did anybody ever had a suture placed, ever? On the face, on the external area somewhere, sutures placed. How many days needs to skin get healed? Some sutures need 7 days, some 10 days. 2 weeks very rare. Month, I wouldn't know. I haven't seen that. But up to 2 weeks, the healing part. Biodegradation, the way we test it out, the way so it's get biodegraded for certain, because by adding different ingredients, we found out one of them biodegrades because they have to stop bleeding, have to give some time of cascade of blood thrombus happens, and a healing process. So we come up with biodegradation within 7 to 8 days. It's natural process of skin healing, not to prevent it, not to move with the nature philosophy, rather than our own adjustment to it. So this our biodegradation, not from ultraviolet light, it's a matter of what we add into it in that mixture, and the time goes for biodegradation. It has its own timing when it gets dissolved. And can we control it? Yes, by ingredients that we add into it. So we come up with certain difference in the biodegradation around from 8, not 7, little less, not enough, from 8 to 2 weeks, from 8 days to 2 weeks. So we have to discover them. So we have to select polymers which will be adhesive to endothelium vascular cells, the one which is loved attached to it. Which polymers out of, not only those biodegradable that you saw, there is different non-biodegradable which can become biodegradable, depends how you change the little structuration formulation. Or adding to it, which we don't want to change the structure, we want to add it to different.
So essentially you have another compound that will start degrading after some time.
Correct. But the time is set up based on timing already. The already timing set up in the next 8 days to 2 weeks, it will be dissolved. Again, it's based on how strong is bleeding and tissue process enzymatic enzymes coming and they dissolve it as well. Their own just body's mechanism. Because they are not immunologically rejected, they accept it. And they accept it as their own body component. Pharmacological compounds structure and has to be structured to respond to bleed. And we did pharmacological study to design a model in vitro, interaction with blood vessels. We tested out before we start getting for the animal study. And we want to look it up. If you put how fast the swelling happens, time necessary to clot formation, which polymers in combination certain generic compounding will match it up for how fast, how large it gets, and addition time necessary to dissolve that thrombus as well. Because the clot, if it stays longer enough, it's because necrosis too. It's very complex. Study was done to find out the best ingredient and best combinations of. And we discovered best candidates for that polymers. We didn't use to larger animals. It's not just rats. We need to go to rabbits and the pigs model. Because it's very complex study that's we involved in. Well, again, if I mentioned to, like in the previous studies, previous presentation, I said to you guys, to find out solutions faster, we use our computer mathematical modeling, which is software was made at the nodule. And that software helps us to match it up different polymers, different generic medications, and see which one will match it and will work for it. Not just match, still has to give us this functionality will match for our needs. And we came up by using software and of course scientists, it's not just software, because everybody wants to AI to be used and don't do nothing. It cook for you and dress for you. No, you still have to use the knowledge and experts to make the decision.
Well, there's one thing, AI is usable after the signal to uncertainty ratio is large enough. Otherwise,
So at least to downsize the
Yes.
purpose of it.
Exactly.
Correct.
Otherwise,
We still need it on this earth.
yes,
right?
otherwise,
Good.
uncertainty is so much.
That is downsizing.
Garbage in and garbage
Correct.
out.
True. I'm not excluding AI. I'm just trying to say it wouldn't be team behind it, it wouldn't come with this solution. So we came up with two components. Gamma K1, we called it K2. Don't ask me why. I'll say that later. Why they're different. So K1, K2 is binary, meaning two components there. As I mentioned here, bipolar. And they are with higher adhesive properties to vascular endothelium, so attract to it. And K1, K2, they are both biodegradable, water soluble, and there's no trace whatsoever left in the body, and no side effects to host body, and it was a very significant results being expected, and it's coming out. Studies that we've done it. If you remember, I mentioned to you guys about calculation times, right? So here we use the rabbit model, and we use K1, K2s. This is central arteries. We call that like femoral veins, or like on level of arteries, large arteries, abdominal, spleen, liver. It's a heavy vasculated organs in our system. You heard a spleen rupture, death imminent. Liver damage is heavy vasculated area, imminent death. Skin, it depends how deep it is, and of course, but we studied on those different most common levels. We call that the medical term head-to-head status, sort of. But again, it was not huge major study as a pharmaceutical does, but we use Silex, which is commonly used right now and approved as a medical device in US Army and for emergency. K1, K2s, our product, and control. You also have a control to avoid the bias. So we use the time bleeding in a minute, and we had parts of the damage. If you see here, Silex time of bleeding was longer, K1 was shorter, and K2 much shorter the time of bleeding. But both of them were efficient. Control actually, I'll tell you what control. Those animals, when they've done the cuts, 2 centimeter cuts, they'll let them bleed until it's dead. It is what it is. So we have to see if it's natural coagulation, as you mentioned, cascade will interfere. None of them survive, especially the large vessels. So it works, but it doesn't. So nature, your own cascade takes later and not significant enough to stop the bleed. And spleen, they both are great, our products. Very similar here. And as you can see, our products stop bleeding faster than existing, and control is not even comparable. Then sorption. Sorption, it's 2 processes going on here. We have a percentage of liquid absorption, and we have a largest volume liquid per minute, K1, K2s. And you can see from here, Silex, the least sorption efficacy it has, just granular, it doesn't have much sorption efficacy. Our 2 products is the best sorption. And I didn't mention this, it's another product, Hemostatic. It's used in military on the beginning, not much used nowadays, but we still use that product because one of the first products came up on the market, so we said, let's test it out. Because Silex and Quick Clot, the other product, is almost similar. So we just used one of the products and added Hemostatic to it. Effective generation. So previously we mentioned about rate of blood stopping, sorption, and this is wound healing. Anytime you happen to, you guys do, when you come up with something, you're planning to do one, suddenly you come up, not different, but something additional to it. What that means. When we would start using this K1, K2 for those wounds, scientists said on 4th day, on 3rd and 4th day, K2 wounds are getting, because we're measuring the size of wounds as well. Wounds getting smaller, and K1, it's also getting, it narrows down, but not as significant as K2s. Then on day 9, so they noticed on K2s, wounds was healing faster than the K1s. Because those 2 gammas, we call the gamma one word, but they have a different additives to it. K1 and K2 has some similarity. K2 has one more additive to it, which brought us to the new discovery here, where we have K2, K1, Silex, and control again, on wound healing in centimeters. Has an influence on the wound healing. So we, besides stopping bleeding, I'm not prioritize this, but they came up with new idea with this one especially on wound healing. So we can use, besides the bleeding, this composition we took away now, and science is working on a new type of functionality like diabetic ulcers, wounds, post-op, to heal it faster. So this is a separate topic, not today.
The question is, how do you know where to put it for an internal organ? Because many of these injuries
just being ruptured organs, right? Great point. All the injuries where you can put the splint on it, they're easy, those straightforward. When it comes to damaged wounds with the ruptures and that nature, you say where to put, you put right on the bleeding spot, on the bleeding area. That's what done with animal-based. On the pig we had it very sharp. We had a knife cut, as happens, in real life, or we had a ruptured way on the spleen. Spleen and liver was devastating, the most, that's the bleeding the most. If you just put an amount of powder in it, and it's within like a minute of seconds, they have a timing there. They stop to bleed, it becomes one large gel. But where to put? Correct. But yeah, it's external, you put on external, but if it's deep enough, good point. They come up with pistol, like a series like, great point. If it's deep, let's say its bullet went through, and it's bleeding inside, you have to get that, how to deliver it. This is just technicality. Delivery is not that hard because they come up with a different type of pistol with the preset powder in it. You just put to directional and you squeeze it in, and the powder goes right there. And well, powder figured out where's in the delivery, it's going to get attracted to it. But that's the delivery method, not the product. But a good point, yes. It could be delivered. Is it hard? It's doable, but this one's the most tough one we had it to go through it, to be honest, this one. So, as I said, K1, K2, they was a great product. They're definitely better, and I show how better they are. So we have gamma, the advantage of gamma on current hemostatic. We have stronger biocompatibility with body tissue. Therefore, we don't have no allergic reaction, no immunologic reactions, no necrosis, accepted very well. It does not cause burn, neither crystallization, neither any granulations. It is biodegradable. It does not need to be removed from the wound. What's happened with the silex, it's not a story. We read a lot of articles, comments from soldiers, from surgical wards. I spoke with my colleagues. They said if the person doesn't get to the hospital or medical service within an hour or two, that basically he survives, but has to be scooped out. That material, like one of those quick laparoscopes. Besides the scooped it out, they damage surrounding tissue. They survive. It works. It does their own job. But unfortunately, it takes much longer time to get healed or end up with the imminent damage. So we don't want that. So always biodegradable, does not need removal from the wound, absolutely not. And contains inexpensive cost effectiveness, remember? That's another thing. Inexpensive raw material, and the composition with additional other generic synergistic combinations. And we do have also natural semi-synthetic polymers. It's like similar that those products done, but with different combinations. And it does absorb 70 times of amount of blood that exists in product, much faster, very quick, and easy to manufacture, and do not need sterilization. Yes?
On the number 2 there, that means that this is not so exothermic as
Yes,
before?
it's not
Why
exothermic.
not causing the burn?
It's not exothermic, right? And what other question?
So it's not exothermic, so it doesn't cause the burn?
No, it doesn't,
Not
absolutely.
like the,
Not the proof, absolutely. It doesn't irritate the skin, it doesn't reject it by tissue, and it's not exothermic, absolutely not.
so if
And
you have to put it inside the body, like you said, there's.
inside the body, on
Or
top of the
burn.
bleeding site, you need to have a contact with blood. And if you have a contact with bleeding area, it gets their own attraction to endothelium of the cell. So it does their own job. If you put it right on time, and the good about it, you don't have to get the soldier or within a certain time. I mean, you have to, it's better, but again, where you have that luck that somebody will take you on a certain timing. It's a reality of the life, let's speak for what we have nowadays and always. So we come up with this great approach, great product. And what do we do nowadays? Where it can be used? Well, all the above. It could be used in military, of course, on our everyday life, trauma centers, acute bleeding surgeons. It could be placed in the acute kits in the cars, in case you got a car accident or something happens on the go. It could be like an acute kit amount to carry it out, and it's a first response situation in ambulances. And as we spoke before, everything needs to be protected. So that's what we have. We have IP behind it of this project. We have, I didn't put the publication, we have publications on it as well. As a matter of fact, yes, that's the recent publication we had. Creation of new medical drugs on based on computer mathematical and also machine, right? So there's a publication and we have an IP behind it. And well, we spoke about our pipelines, yes.
So, does that mean that the first aid kit providers have accepted this product
Okay.
instead of Band-Aids, or?
No, Band-Aids, they have our own purpose to be used.
Right, I mean,
This product for, if you cannot stop the bleeding, harsh bleeding, or bleeding which is damaged on the level of the vessels that you cannot calculate or band-aid it,
yeah.
then you can utilize this. Yes.
What about loss of limb?
Perfect. Loss of limb, yes, like same thing. Whole vessels or structure exposed. Absolutely, it could be applied on it again. Have we done on it? I don't really remember, but that's a good question. I have to look it up. No, we didn't. I have to check with the scientists. We done mostly like those spleen, internal organs, but this is a great point.
Like a slashing or a bullet or something like that.
Absolutely. Great point. Yes, I'll check on it. Yes.
You mentioned you use trees. Just based on what you told us, it seems to me that maybe the most valuable part of trees was getting attention to the contradictions. Is that true?
Well, it's true as well, but we don't forget about principles too.
Yeah.
Without contradictions, without questioning, without debate, you cannot get to the principles. Because by having contradictions, having battle we have, and talking with the scientists and the trees experts, principles applies later.
Yes.
First, we have to figure it out where are the Achilles part, what is missing from the entire picture. Then we're going to put together, then we say, okay, how to solve the problem. Then we get to the principles which you can apply to the situation and gives us direction to scientists, and myself including, to give more ideas. So we're supplying more ideas, and then trees experts say, okay, you just nailed it. Now let's get this part to the next level, and you guys figure it out. What other element could be, make the swelling up, for example, make it at the right time? Which element will make it dissolve? You guys had it for 5 days, no good. You just said it, like I said, suture dissolves in 7 days. Kleyn said in 7 days, come on guys, work it out for 8 days. So that's the trees part coming over to help us out to understand how to move to the next step, basically. But it's great teamwork, and I guess without it, we couldn't come up with any accomplishment. So this one, we spoke to from previous, presentation, that our pipelines, we mentioned about polymyxin, and I spoke before lunch, and multi-resistant bacteria. That was the question we had. What you do with polymyxin, right? If it's resistant, then what? The leftovers that Dr.Farber mentioned, what do you do with that? When the bacteria is resistant to polymyxin, then what to do with those bacteria? You can hug them, you can walk with them, or you can battle with them. You will be surprised the answer. Hemostatic I just presented to you, and TB, that's another project we're working on, and it's ongoing. And we have another project which basically we done, we just haven't brought it up to public level yet. I guess let me see what is next there. Yeah, that's us. Any questions? Yes.
Is this product on the market today? Did I go buy some of this or not?
Good point.
Because I'm thinking.
This,
of a place like
this product not on the market yet, although there's a much higher chances compared to if you do just drugs, for example, right? Because we did some due diligence on our end on medical devices, because it is medical device, because Silux and the QuickLot belong to other group medical devices. And it goes to the FDA through, then, patent lawyer can help me out or just let us know, but overall, to FDA, make it faster. Not fast enough, but easier, sort of. So device, it's applied as a device part than drugs, right? Drugs more expensive, more processing. So we hopefully, our only dilemma right now, not dilemma, is basically we're already working on it. So we're applying to meeting with investors. We just spoke to a colleague here. We're trying to meet with pharmaceuticals, right? Who making those generics, the one we apply to, because for them, it's new opportunity repurposing drugs. Because if this drug was used for something else, why not to apply another usage? And that's will help us to get to the next level to utilize this for the public and go to production as well, of course.
You're talking to some of the generic producers in Europe, in this country.
Good point. We looked upon, as I mentioned prior to lunch, we just started coming up to the US market, in general market last year. Till then, we were doing science, with my work. Now I dedicate practically 50% of my career in science, thank God. So, looking forward for 80 and 90 and 100. So, what you just said, just mentioned Europe, we looked upon Europe as well. In Europe, it's simpler to get that medical device, simpler, not simple, but simpler to get approved. But again, we need additional data to put together, and we're looking forward for that part as well. Because if we get as a matter of fact, if you look at the Silux, originally was approved in Europe first. Then they brought up to the military market later on, the US market. So we're looking for the patent in other companies so we don't do same mistakes. You learn from, it's better to learn somebody's mistakes than your own.
Any other questions?
No?